To the physics colloquium, and today we are happy to have Dr. Matteo Barglia from the New York University, and and he's here as a part of this RELIC, Reconstructing Early and Late Events in Cosmology, RELIC Indo-Italy program, and he visited last year as well. So I know Matteo from a long time during my postdoc days in Bologna, INFN. And he was a PhD student at that time, working with Professor Fabio Finelli there. He worked on modified gravities, and we started working on something on primordial features. He mainly works on early universe. He worked on modified gravity and features and few other things related to inflationary physics and primordial magnetic fields as well. And he has written quite impactful papers, several impactful papers, well-cited papers on in that directions. After Bologna, he joined IFT Madrid as a postdoctoral fellow, and after IFT he moved to US, and presently he is a postdoc at the New York University, and today he's going to talk about the tastes of inflation from the largest to the smallest scales. So I'll leave the floor to Matteo.
Thanks, Siraj. Can you hear me well? All right. Okay. Good morning. So my talk is going to be a little bit long, and I hope that I will manage to get to the end. And the main reason is that I'm trying to give an overview of all the works that I did with my collaborators. Some of these collaborators are sitting here in this room. And as the title says, I'm mainly going to talk about phenomenological and observational tests of inflation. And I divided the talk in these two parts. One is related to large-scale tests, and the other one is related to small-scale tests. And the nice feature of the talk is that it is compartmentalized. So if I don't get to the end, we can stop at any point, and there won't be any damage to the logical flow. It's going to be pedagogical, so please let me know if you find it too pedagogical and I can skip the introduction, okay? And I'm going to start from part one by introducing the concept of primordial features, okay? So primordial features are a signature of some beyond vanilla model of inflation, okay? And I will define them in a second, and then I will go on to present some constraints on these non-standard signals from the cosmic microwave background, and forecast for future cosmic microwave background experiments. Then I will move on to small-scale tests. Okay, so the small scales are a little bit more of an uncharted territory, and in particular I will talk about gravitational waves. How to test inflation with gravitational waves at small scales. So I'm not talking gravitational waves at large scales that can be tested with the CMB. I will present some upper bounds from CMB, but CMB spectral distortions rather than anisotropies. I will then go back to the theory and present some of the models that can be tested with these observations. And then, if time permits, I will talk a little bit about some issues with perturbativity that I am sure that people are interested in here. But this is more, I'm not sure I'm going to be able to talk about that in 1 hour. We can discuss that over lunch if anyone is interested. Okay, but let me start with part one. So again, I'm going to start with a very pedagogical introduction. Please let me know if you want to skip it. Why cosmic inflation? Essentially, cosmic inflation was engineered to solve this kind of problem that you see here. Okay, so if you look at the CMB map on the sky, okay, of course you do see anisotropies, but the CMB is largely homogeneous and isotropic, okay? And if you take 2 points in the sky of the CMB, it is possible that, so for example, if you look ahead and then you look in the opposite direction, then if you follow the standard Big Bang scenario history of our universe, then these 2 points would have never been in causal contact, okay? So here's where inflation comes to the rescue, okay, by postulating an initial phase of accelerated expansion, okay, so that the Big Bang singularity is pushed to negative conformal times, and these 2 points have more time to communicate in the past. Okay, so this is the initial motivation behind inflation. Okay, and the way inflation is usually embedded in a physical model is through a scalar field, okay, that slowly rolls down a potential, okay? Then eventually this is the reheating phase that is needed to produce standard model particles, but I won't be concerned about that. And I will only talk about the initial stages of inflation, okay, where the inflaton slowly rolls down a potential, okay? So this is what the model looks like, okay? We are requiring isotropy and the homogeneity of the universe, so this is the kind of metric that we are considering. With this requirement, the scalar field has to depend only on time. It cannot depend on position, otherwise it would violate the homogeneity and the isotropy of the universe. And taking this simple Lagrangian of a minimally coupled scalar field, these are the field equations, okay, once you assume this profile for the scalar field. Okay, so we have the Friedmann equation and the Klein-Gordon equation. Okay, now the condition for the universe to accelerate is this one. Okay, so the first derivative of the Hubble radius divided by its squared must be smaller than 1. It can be shown, it's easy to show that this is equivalent to an accelerated expansion, okay? But we want the inflation to last long enough, and so we usually impose a tower of conditions that are usually referred to as slow roll conditions, okay? So the epsilon parameter and its logarithmic derivatives must be smaller than 1. In this case, we can neglect the acceleration of the scalar field, and the Klein-Gordon equation can be solved analytically, okay? This is a very significant simplification. And this is essentially, and you can see that this can be essentially translated into a condition on phi dot squared, which is the kinetic energy of, and the velocity of the scalar field. Okay, so this explains the name slow roll inflation, okay? And in turn, using the Klein-Gordon equation, this can be translated into a condition on the scalar field potential that must be flat enough for the universe to inflate, okay? So this is slow roll inflation. This is the background of slow roll inflation. But we do know that this scalar field is actually a quantum field, okay? So on top of this background, we do have quantum fluctuations, okay? These quantum fluctuations source metric fluctuations, okay? In this particular case, the metric fluctuation takes this form, okay? So we have a scalar and the gravitational wave, so a tensor fluctuation, okay? And this is how this so-called curvatory perturbation, which is an important variable in inflationary cosmology, is related to the fluctuations in the scalar field, okay? We can quantize this scalar field using very standard techniques of quantum field theory in curved space-time, okay? And we can compute an important quantity, which is the power spectrum of these scalar fluctuations. All right. Now, why is this power spectrum important? So this is essentially the kind of evolution that a comoving, that a quantum fluctuation with a given comoving wavelength undergoes, okay? So you see that by definition, the comoving wavelength of the quantum fluctuations is constant, okay? Which means that its physical wavelength is stretched during inflation, during this accelerated expansion, okay? Whereas the point of inflation is to make the comoving wavelength of the Hubble radius decrease with time, okay? So eventually, fluctuations that are inside the Hubble radius, okay, which essentially controls the causally connected regions in the universe, okay, eventually they cross the horizon, they exit the horizon, and they become superhorizon, okay? And it can be shown that when they are well outside the horizon, they behave like classical fields, so they essentially classicalize, okay? But then when the standard Big Bang scenario kicks in, okay, the Hubble radius, the comoving Hubble radius starts growing again, and so these quantum fluctuations that are described as classical stochastic fields, they re-enter the horizon, okay? And gravity essentially mediates these metric perturbations into density perturbations, okay? So density perturbations of electrons, nuclei, dark matter, photons, baryons, whatever, okay? So this is how we see the initial perturbations that eventually collapse under gravity, and later on they form the large-scale structure that we see in the universe, okay? So this is why the primordial power spectrum is a central quantity, because it provides the seeds of the density perturbation at the onset of the radiation-dominated era, okay? Now, how do we compute it? Let me just show you a pedagogical example, okay? So this quantity, the curvature perturbation, is described by this in Fourier space, which is what we need to compute the power spectrum. It is described by this second order differential equation here, okay, where we have defined this zeta, which is given in terms of the epsilon parameter, okay. Again, the epsilon parameter during slow roll inflation can be considered to a very good, to a very accurate extent as a constant, okay. And so this equation can be solved as follows, okay. So it is just a superposition of propagating waves with positive and frequency and negative frequencies, okay. We connect this, we impose some initial conditions, which usually in inflationary cosmology are the Bunch-Davies initial conditions, okay. So the waves, these modes behave as in Minkowski very early on, because their wavelength is much shorter than the Hubble radius, so they do not feel the curvature of the space-time. And so this selects only this C1 to be equal to 1, okay? So we do not have negative frequency states, okay? Therefore, it is very easy to compute the primordial power spectrum, which is essentially a constant, okay? Now, if we do correct this equation, okay, if we do a more refined calculation, we will find that this is not exactly a constant, okay? And we get some so-called slow roll corrections to this, okay? So the primordial power spectrum is essentially described by a power law, okay? Where the spectral index of this power law, which we call historically ns minus 1, okay, is essentially given in terms of these slow roll parameters, okay? So a very important prediction of slow roll inflation is that it predicts ns, which is almost equal to 1, but not quite, okay? It is not exactly equal to 1. Now, again, because of gravity, because gravity mediates these primordial fluctuations into density perturbations, okay, we can observe these primordial fluctuations into the CMB, and in particular, the angular power spectrum of the CMB is given by this very simple convolution here, okay? So you see that the primordial information enters here, and then everything that concerns the later evolution of the universe is encoded by this simple transfer function here, okay? So this is the only place where primordial information can affect the computation of angular power spectrum, okay? And these are the effects of the tilt and of the amplitude. We have very accurate data from the Planck mission, and so we can constrain this model. Okay, just a clarification. On the y-axis, okay, we have the tensor to scalar ratio. Also, gravitational wave fluctuations are produced during inflation, and this is how we parameterize the ratio of their power spectrum to the scalar power spectrum. Okay, so this two-dimensional plane is a classical way to see whether a slow roll model of inflation is in agreement with data or not. So you can see that some of the models are already, first of all, you see that ns equal to 1, which corresponds to the jitter, is excluded, okay? So inflation is very well consistent, slow roll inflation is very well consistent with data, but the data are precise enough that you can already rule out some of its implementations, okay? So far, this is the vanilla scenario for inflation, okay, slow roll inflation. But then I will move to more non-standard scenarios, and theoretically there is a motivation to do so, okay? So if you imagine, okay, inflation being embedded in some UV complexion, usually these UV completions come along with not just one field, but more scalar fields or vector or fermion fields or whatever. But anyway, so in a two-dimensional plane, you could imagine slow roll inflation as something like this. Okay, so essentially the trajectory has found a very shallow and straight path of valley, okay, which is sort of protected at very high barriers, okay, which this would be like the very massive fields, okay, and so this is a kind of fine-tuned trajectory, okay, because in principle you could expect even something like this, okay. So you see that in less fine-tuned scenarios, you could have things like bumps, turns, very sharp turns in these trajectories. And anytime this happens, okay, this doesn't mean that you stop inflating, okay, so epsilon can be still smaller than 1, but you generically violate this tower temporarily you violate this tower of slow roll conditions, okay? So then the question is, how does this violation of slow roll conditions translate into the power spectrum, okay? And to show that, I will start with a very simple example, which was invented by Starobinsky back in 1992. Okay, so a warning, this is not Starobinsky inflation. It's another paper by Starobinsky, okay, where he considered what happens when you have like 2 stages of inflation, okay? And these 2 stages of inflation are essentially, so you have 2 attractors, one here and one in this region, okay? So you have slow roll inflation here and slow roll inflation here, but essentially they are connected by a sharp feature, okay? In each of a sharp feature, for example, in the potential, okay? It could be anything else. It could be a sharp feature in the internal field space of this scalar field or whatever. But the thing is, you have 2 slow roll regions, and one has a different first slow roll parameter than the other, okay? So if you follow the calculation carries on exactly as in the previous case, okay? So you could imagine, and because the amplitude, the overall amplitude of the power spectrum scales like 1 over epsilon, okay? So the final result is something like this, okay? So you have different amplitudes before and after this transition. Okay, but this is in fact not the final result, because I have overlooked a very important point. Okay, so in principle, the solution for this curvature perturbation is a superposition of a positive and negative frequency waves. Okay, so the solution in the in region, okay, is matched to the initial conditions, and so this solution is okay. But this one, okay, in principle, there is no reason to put this C2 to 0 this time. And this C2 and C1 are completely specified by matching conditions at this point, okay? If you follow the calculation, you would find that this C2 has this specific oscillatory form, okay? And the frequency here of this exponential or sinusoidal or cosine term or whatever is set by the scale that crosses the horizon at the time of the transition between the 2 slow roll regions, okay? So what happens is that, yes, the intuition that I had before is okay. So in the far attractor regions, I do have different amplitudes, but then around the transition, I excite some oscillations in the primordial power spectrum. So these are what I will refer to as primordial features, okay? So signatures, oscillating signatures in the primordial power spectrum, okay? And it turns out, so this is a very old, it's a 30 years old model that, by the way, is still catching on nowadays for other reasons, though, that I will probably explain in the following part of my talk. But it is actually a generic feature. So anytime you have a transient departure from a background quantity during the inflation, okay, you excite this oscillation in the primordial power spectrum, okay? And this oscillation has what I call running, which takes this form. Okay. Of course, depending on the very specific incarnation of this mechanism, okay, you could have different envelopes of this running, okay, so scale-dependent amplitudes of the running, okay, as is shown in this plot here. So this is the case that I showed before, but we could have something different, like a step in the potential or a bump in the potential, or even implement a sharp turn in the trajectory if we have more scalar fields, okay. But anytime you have such a sharp turn, you do induce this specific running in the primordial power spectrum, okay, followed by a different, multiplied by an amplitude which is more model dependent. Okay? Now this is one specific kind of feature during inflation. In principle, you could have something different. Okay? Instead of having something like a click, like a sharp feature, which is momentaneous, you could have something like a periodic modulation of the background during inflation. Okay? And this is what we call usually a resonant feature, and this would cause a different running for this feature signal. Okay? Instead of having a sine k, we would have something like a sine log k. Okay? And there is a yet different kind of feature, which is what we usually refer to primordial standard clock feature, okay, which is more of a superposition of these two kind of features. Okay, so this is, for example, this is an illustrative example of what I mean. So, for example, you have something like a slow roll here, and then you have a tachyonic falling into this potential well. Okay, so here at this point you excite a sharp feature. Okay, but then you excite also the oscillations of a massive field, okay, and this provide you with the periodic modulation of the background. And so this sharp feature signal is followed by a damped resonant feature signal like the one I showed before, okay. So this is another example which is more of a superposition of these two models. Okay, so this is more or less the zoology of features in the primordial power spectrum that you can have during inflation, okay? But then the question is, since we're going to talk about the CMB, is the CMB sensitive to this kind of signals, of this kind of primordial signals? And the question is yes, but it really depends on the frequency of these signals. And the reason is the following. So as I showed before, the CMB angular power spectrum are a convolution of this primordial power spectrum, okay? And the window function is what we call the transfer function, okay? So at any multiple, we have a different transfer function which depends on k. And this is an example of a couple of multiples, okay? And you see that essentially they are very peaked around the main scale, which corresponds to the peak of these Bessel functions, okay? And in a very rough way, we can model them as step functions like this, okay? And essentially anything that varies slowly over this step function is something that you can test. But if the frequency is too high, okay, it will be washed out in the convolution, okay? So essentially, as you go to higher multiples, okay, if your frequency is fixed, you are less sensitive to these features. Okay, and let me stress the fact that this is the transfer functions for temperature. These are the transfer functions for E-mode polarization, and you see that the E-mode polarization transfer functions are their width is thinner. Okay, so in principle, the E-modes are a better detector of this kind of signals. Okay, and this is an example for sine k or sine log k. Okay, so you see that depending, so for example, sine k, you see that if you show them, if you plot them in log, you see that the distance between the peaks gets closer and closer as you go to smaller scales, which means that they will be harder to detect as you move to higher multiples, which is precisely what you see in these residual plots here. Whereas for sine log k, things are different. The sensitivity of the CMB angular power spectrum gets better as you go to higher multiples. Okay, so this is showing that CMB angular power spectra are sensitive in different ways to different physical mechanisms producing these primordial features. Okay, so this is all theory, but how about the data? Because we do have data. Okay.
You said in the previous couple of slides back that the simpler sine feature is non-tested.
Did I say so?
Yeah, in the slide. Can you go a couple of slides back?
No. This is it's the same feature with different frequencies. Okay. So what I'm saying is take this. Okay. Suppose that this is at a given L. Okay. You zoom in like here. Suppose you zoom here. Okay. You can model this as a step function, more or less. It's just a rough, intuitive picture, okay? If your feature has a very high frequency, then at that multiple you cannot test it. But if it has a slow, it's all a matter of a trade-off between frequencies and multiples. All right, back to the data. So these are the temperature data from Planck, which are the only ones that are mapped down to cosmic variance. Okay, so any search for a feature will essentially try to fit this data. Okay, now we're getting better data in E modes, and that we talk about in the following. But let me start just from here. Okay, so historically, this is where people have been looking for features. Okay, very large scales, so small multiples. Okay, and the reason is that you see that there is a generic suppression of power here. Okay, so these are the residuals. So the data vs the lambda CDM model. Okay. And also observers, they usually refer to this as the Lowell multiple, okay? And they do not make any distinction between any range of multiples within this area here, okay, within this region. But then, from the point of view of inflationary model builders, they are assuming, I mean, this, for example, a step in the potential can fit this region here around L equal to 20, okay? Let me just stress that these are just anomalies. They are not things that are detected with extremely high significance, okay? But this, again, could be fitted by something like a step in the potential, as I showed before. Other models, such as this is something that I'm showing from a paper by Diraj, like the Starobinsky model, okay? This is a model by Diraj, but it's very similar. The mechanism producing the feature is similar to the Starobinsky one. They can instead fit multiples smaller than 10, okay? And in fact, it is an interesting question whether with future experiments we will be able to tell these two kind of models apart. And this is something that we are currently exploring, but we do not have interesting updates on this, okay? So this is historically what has been done, okay? But then after the advent of Planck, and the reason is that this is something that was observed even with WMAP, okay? Then with Planck, we got a better handle on the high multiples as well, so smaller scales, okay? And you can see clearly that there is some sort of residual pattern also here. Again, not something which is statistically significant, but in principle, you could ask whether this model can provide a better fit to the data, okay? And that's what we did. So we considered a sample of very popular feature models, okay? Let me stress that here what we do is we really start by modeling the feature in the Lagrangian. So we really put a feature in the potential, for example, in this case, or in the field space, in these two cases that are multi-field models of inflation, okay? And we built a pipeline to numerically evaluate the power spectrum because it cannot be evaluated analytically. At least so far, there haven't been any analytical solutions especially for these multi-field models, okay? Numerically evaluate the power spectrum, plug it into the Einstein-Boltzmann solvers, compute the CMB power spectra, and then compare them to data, okay? So we did this comparison to Planck data, and this is what we found, okay? Let me stress that it was a full Bayesian comparison, and here I'm just showing the best fit to the data. And these are the best fit candidates that we found, okay? And this is like a snapshot of their fit to temperature and polarization, and E-mode polarization data, okay? And so we found the chi-square to improve by quite a lot, and specifically this primordial standard clock model that mixes sharp and resonant feature is the one that provides the best fit to the data to date, okay? All these models are 3 parameter extensions to lambda CDM, by the way, because you need a parameter to describe the amplitude of the signal, one to describe its location, and the other one to describe its frequency, okay? But then the problem is that there is no statistical significance for these features, okay? So what I mean by that is that if you compute the base factor, okay, the base factor is just a quantifier for model selection that tells you whether the model itself is preferred over the baseline model, then this is just not significant, okay? It's not saying that these models are disfavored with a very high significance, but there is no way to favor them over the lambda CDM either, okay? But then this may be just because the data are not powerful enough to identify this as the true model of the universe. And so we explored whether with future data we will get a better, we will be able to detect these models or even rule them out. Okay, and the reason is that there are many planned CMB experiments. For sure, this is not going to happen. Simon Observatory is not going to be to happen in 2023 because 2023 is almost over. But essentially, we have this plan, Simon's Observatory, which is a ground-based experiment. Okay, a ground-based telescope. So this will be able to map the smaller scales. Okay. And then Lightbird is going to fly, mapping the larger scales, and then eventually CMBS4, which will be an array of Simon observatories, essentially. Okay, and this will map again the small scales. All these experiments will provide an accurate measurement of E-mode polarization. Okay, almost down to a small to scaling. What's it called? Okay, for cosmic variance, right? Sorry, just a slip of the tongue. And so, because E-modes are a better detector of the signals, okay, they will provide definitely a very good handle on these kind of signals, okay. Let me show you as an example this CPS-C model, which is the one providing the best fit to the data. So if you look at the posterior distribution of the model parameter with Planck only, you see that essentially we are not detecting anything. So yes, it does provide a good fit to the data, but this explains why it is not statistically favored, because its parameters are only constrained, but they are not detected, okay? But then with future experiments, starting from Planck plus the addition of small scale data from Simon Observatory, we will be able to shrink the error bars down to a detection when the full array of Planck, Lightbird, and S4 is operational. So you will, in the context of this, just to give you an idea of what this detection would mean in the case, in the context of this model, we will be able, so because in this model the feature is produced by a massive field classically oscillating in the background, this detection would amount of a detection of a massive field with a mass which is 1,800 times the Hubble rate during inflation, okay? And this 18 doesn't carry any particular meaning, it's just what the data are pointing to, of course. And it will be like a more than 5 sigma detection, okay? Of course, this is a forecast, so it is always optimistic. We are assuming a fiducial model, of course, but it is a very interesting science that we can do with future CMB experiments, okay? And this is just a table that shows how we will be able to rule out other feature models, as well as the standard scale invariant power spectrum, okay? Now, this is all with the CMB. I have never worked on the large-scale structure, but this is definitely something that is going to be interesting. And there are already some, though it is a tricky business to compare these models to large-scale structure, because CMB is linear, whereas large-scale structure is highly nonlinear, and so you have to perform a nonlinear modeling, which I'm not an expert of, but people have worked on that, and there are interesting results on this side as well. And looking at in the context of my works, what is really nice to see is that this best fit that we get is actually a mode of the posterior distributions from the analysis with large-scale structure as well. So you see that there is some sort of indication for this best fit already in large-scale structure. So like performing a cross analysis between CMB and LSS would be extremely interesting. And of course, there are high hopes to constrain these models with future experiments like Euclid as well. I mean, Euclid is already in the space, but I don't know when the data are going to become available. All right, so this was all about part 1, and I went quite fast, so there should be time for part 2. But before I move to this part, which is quite different, are there any questions?
So you always mention about this power spectrum where you haven't seen, but after the inflation there will also be heating and all that, not affect your power spectrum.
So reheating, so in principle, no, and the reason is that it's this one. Okay, so maybe it's hard for me to go back to the very beginning of the thought, but so there is a reason why we are able to make predictions from inflation, and the reason, and it is precisely the reason I am considering this curvature perturbation variable. Okay. Essentially, this curvature perturbation is conserved on superhorizon scales, okay? Which means that once it has crossed the horizon, okay, it shouldn't be affected by reheating. Of course, this is modulo some caveats. I'm sure there are some models of reheating but there is a large separation of scales, okay? So the scales that we are testing with the CMB are those who cross the horizon a long time before reheating, okay? So all this perturbation, by the time by the onset of reheating, they have been superhorizon for a long time, okay? So they're not in causal contact with what's happening inside the horizon, okay? So this is the reason why we are able to make predictions out of inflation.
Thanks.
But reheating does affect actually the CMB, okay, somehow, especially through the way the pivot scale is computed, okay? So depending how long the reheating phase lasts, okay, the pivot scale which is computed is different, okay? So it would provide a shift of this power spectrum, which we didn't consider in this work, by the way.
Can I make a remark?
Sure, absolutely.
I understand that simple reheating mechanisms will not affect the scales, affect the features on large scales. But if there is, what will be the implications for your constraints, etc., if say a curvaton scenario just raises the overall amplitude by say few percentage, will it affect the fit, so to say?
So if it's just a shift in the overall amplitude. Then no.
It will not affect the.
It will not affect it. I mean, it will be just a shift in the central values for our constraint.
And you have allowed adequate room for the shift in the pivot scale.
No, that we didn't allow. We just fixed it.
Okay.
But it could be done. It would just create an additional degeneracy line.
So you don't see any effects on the fits, in terms of overall scaling or sliding slightly?
No, we do.
Okay.
I'm just saying that if we are allowing only the overall scale,
okay,
and the sliding, okay, but that comes from this model. If there was an additional one, then there would be like almost a perfect degeneracy, which we wouldn't able to constrain. Of course, I guess that, if one were to model reheating perfectly, you would have like also effects on the effective number of relativistic neutrinos, so relativistic spaces. So you could sort of break down that degeneracy, but it would be complicated, of course. So yeah, I would be in favor of adding reheating to this analysis only once you have a very specific mechanism of reheating you have control on, and so you have multiple predictions.
The challenge is that those scales are going to be very difficult to test.
Yes.
So we are not going to have any constraints on reheating in the near future. Okay.
I know.
Okay.
Yeah, I guess there may be some other predictions from reheating on high frequency gravitational waves or whatever. This is why more people work on inflation than those working on reheating, right? Or then there are people who work on both of them, like you. But if I look at your Inspire page, there are many more papers on inflation than reheating, of course. Okay. So if there are no more questions, I can go to part 2, which again is a little bit more futuristic. While I took a phenomenological, sure, I did take a phenomenological approach in my first part, but here it's going to be even more phenomenological. So I'm just going to parameterize things, okay? And the reason is the following, okay? So these are the constraints that we have at very large scales, okay? And then at small scales, okay, which corresponds to larger wave numbers, essentially, up until a couple of years ago, let's say, not just, 10 years ago, I don't know, there were no constraints at all on the primordial power spectrum, okay? So this is completely an uncharted territory, okay? So anything could happen here, essentially, okay? And I remind you that these scales correspond to mechanisms, to things happening at a later time during inflation compared to what we are testing with the CMB or anyway large-scale structural data, okay? So at those scales, we have only, as far as my understanding is concerned, well, there is also another observable that I am not reporting here, which is 21 centimeter, but this is more futuristic, okay? So we have only 2 handles on the primordial power spectrum. One is CMB spectral distortions, and the other one is gravitational waves, okay? So again, like I said, anything could happen in between, okay? And in fact, if we want to hope to detect any signal from inflation, okay, because of the lower sensitivity of the 2 observables to the power spectrum, we need some drastic enhancement of the primordial power spectrum, okay? So the small amplitude kind of features that I showed before, we cannot hope to detect them with future measurements at small scales, okay? And we need something which is way more drastic, okay, to hope to be detected, okay? Now let me start from gravitational waves, okay? Because this is a different observable than what I've been talking about before. And this is actually an indirect kind of observable, okay? So when we have a large enhancement like the one I showed before, okay, what happens is that the linear perturbation theory that we use to compute inflationary observables can break down, and we start having second-order effects, which become important, okay? So at second-order perturbation theory, we can source what we usually call scalar-induced gravitational waves, okay? And these scalar-induced gravitational waves, they take this form. This is their energy density, okay? It's essentially a double convolution of the primordial power spectrum, okay? Now, let me just parameterize the form of this bump in the primordial power spectrum of scalar fluctuations for simplicity, okay? And then I will talk about what realistic models would look like, okay? Let us suppose that we have like a Gaussian in log k field space, okay? That is a log normal essentially, okay? If we inject into this kind of, into this equation here, a log normal which takes this form, okay, and depends on 3 parameters, this is what we get, okay? So you can see that as the width of the log normal is large, we get essentially another log normal in the omega GW space. But as it becomes narrower and narrower, we get this specific double peak kind of structure, okay? So we induce a stochastic gravitational wave background with this very specific spectral shape, okay? Now the question is this going to be detectable or not? And there are many proposed experiments, okay, in the future that hope to test gravitational wave backgrounds, starting from very large scales. We have, of course, Planck. Okay, sorry, this is not, yeah, this is Planck, but I wanted to put Lightberg here, which goes a little bit down. But this is not what I mean, this is a different kind of gravitational waves that we are testing, okay? So these are the tensor to scalar ratio type of gravitational waves that I talked about. Now I'm going to talk about a significantly larger amplitude stochastic gravitational wave background, which can be detected at small scales, okay? So what we will be interested in is, starting from small scales, is, for example, gravitational wave-based, ground-based gravitational wave experiments, okay? So people have been looking for this type of gravitational wave backgrounds in the LIGO band. Of course, nothing was detected, but this is just to show that you can already put some upper bounds on this type of backgrounds, okay? Which then, if you are lucky, you can translate into bounds on the primordial power spectrum of scalar fluctuations. Of course, this is a very much indirect probe of the primordial power spectrum. And then with future experiments, such as, for example, updates of LIGO or Einstein telescope that is going to be built in Europe, you can push this upper bound down, or if anything is lying in between, you can even hope to detect it. Okay, so this is very high frequency, so very small scales. Okay, if we go back to less small, so to slightly larger scales, which means smaller frequencies. Okay, we have LISA. Okay, LISA is going to test the millihertz band, and this is something that we are doing together with the LISA collaboration. Hopefully, this paper will be out. So there are not so many details because this is not something that I could share, but you can see that that this kind of gravitational wave backgrounds can in principle be tested with LISA. And let me just mention that in this forecast we correctly included all the extragalactic foregrounds and galactic foregrounds that we expect in this specific band. So there are high hopes to detect this with LISA, which which has a sensitivity that is much better compared to LIGO. Okay, and then there are actually already some indications of these gravitational wave backgrounds in PTAs. Okay, as many of you probably knows, there has been an announcement of a detection of a gravitational wave background from PTA experiments. Usually people refer to as nanograph, but there were also EPTA and the Parkes collaboration in Australia, and also the Indian and Chinese collaborations as well. And this kind of stochastic gravitational wave background is actually the one that is providing the best fit to the data. Actually, it is very interesting to see how if you add a background in the analysis, if you add a background from supermassive black holes, which is the source which is expected to be there in the nanohertz region, this is not affecting the analysis at all, because the data would prefer anyway the presence of this log normal kind of gravitational wave background into data. Of course, there are some problems with physics. So, for example, which I don't want to talk about now, but we can discuss at the very end. Like, for example, overproduction of primordial black holes. So the amplitude of because the reason is the following. Okay, so if you want to fit the nanograph data with this kind of gravitational wave background, essentially the region of this background which is fitting the data is the tail of the peak. Okay, that implies that the overall amplitude of the peak must be quite large. So the overall amplitude of the peak in the primordial power spectrum generating this gravitational wave background must be very large, okay? And so you can run into problems with gravitational wave productions. But from just a very agnostic point of view, this provides the best fit to the PTA data, okay?
So what's the problem with higher peaks?
So the amplitude is very large.
How large?
It's as large, so you can read it off from here, right? So it's this A is the amplitude of the primordial power spectrum. This is log 10A, so it could be as large as 1.
Close to 1.
No, it's even actually, if you look at here, because you see this is a perfect degeneracy line, because you want to fit the data with the tail, okay? So you have actually a lower bound on the amplitude. Of course, there are some regions that are allowed by the data that can fit the nanograph results quite well, and being in a safe region for overproduction of, where you do not overproduce gravitational primordial black holes. But yes, you see that there is a bulk of support for the posterior distribution in the region with high amplitudes. Okay, but of course, there are many works by people who have invoked like very large negative non-Gaussianities. I mean, it's still under debate. But the nice thing is there could be already some indications of these gravitational wave backgrounds from inflation in the data. Okay? All right, and then there is finally going back to larger scales. So I went all the way down to the smallest scales that are testable, and now we are going back to the CMB. Now, anisotropies are not the only observable that you can measure out of the CMB experiments. Another one is spectral distortions, okay, that are really distortions in the black body spectrum of the CMB, okay? They could be of different types. Usually people consider G-type, mu-type, or Y-type spectral distortions, and in particular, it can be seen. So this is the variation in the intensity spectrum of the CMB. Okay, so you have all different types, and this delta I for each of this G, mu, and Y, which are the coefficients multiplying this specific spectral variation of the intensity, they are an integration over the so-called heating rates, which are in turn a convolution of the primordial power spectrum over some window functions, okay? So the amplitude of these spectral distortions depends on the primordial power spectrum itself, okay? Of course, it is not, these window functions are very, very large, okay? So because of the reason the reason I showed before, since the window functions are extremely large, you cannot hope to test fast varying oscillatory signals, okay? So you are only sensitive to the bulk of this bump into these window functions, okay? But we are essentially, constraining the integrated power spectrum over a range of scales, okay? These are the window functions. So you see that they cover a very large range of wave numbers, okay? And this is more or less an approximation of this A. And these are the constraints that you get essentially on the power spectrum, okay? So this blue region, okay, is the region which is allowed by COBE-FIRAS data, okay, which are the oldest CMP data that we have, okay? And you see that this primordial power spectrum that can fit data, nanograph data, lies safely within this region, okay? You see that you have when you analyze this log normal kind of primordial power spectrum bump against FIRAS data, you see that you are only ruling out some regions of the parameter space, but a large part of it is allowed by the data. Now, the question that we asked is, let's suppose that this nanograph hypothesis is actually representing the true model of the universe. Will future measurements of spectral distortions by, for example, PIXI, which is a planned mission by ESA, I mean, it's not been accepted, but it's something that people have been talking about for a long time. Will these experiments, okay, be able to detect this signal? In principle, you see this is the spectral distortion signal, this is the sensitivity of FIRAS, and this is the sensitivity of PIXI. So in principle, we should be able to detect this spectral distortion signal, okay? And this is, for example, what we get from PIXI, okay? So the answer is, even though this signal will fall into the sensitivity of PIXI, okay, it will be hard to detect this signal. And the reason is the following, okay? So this solid line is the mu type signal, okay? Whereas this dashed line is the Y type signal, okay? So this kind of bump in the primordial power spectrum depends on 3 parameters, but here we're only measuring 1. Okay, so we can improve the constraints, but it will be hard to detect it. However, if we analyze the data from this CMB spectrometer together with PTA, okay, so if we perform a synergy of these 2 data sets, this is what we will get, okay? So we will have like a multi-wavelength kind of synergy, okay? And because we will have an handle of the gravitational wave background at small scales and an handle on the primordial power spectrum at larger scales, we will be able to break all these degeneracies and make a very and get a very tight constraints on the primordial power spectrum. Okay, so this is showing a very specific scientific goal of the synergy of these two experiments, which are far away in terms of wavelengths from each other. Okay.
I understand that picture better. So what you're saying is that as long as the rise is after 10 power 2 megaparsec inverse, the constraints are fine. I mean, it will satisfy the spectral constraints from spectral distortion, even at the level of Pixie. That's the bottom line?
No. What I'm saying is the following. So if you take take the blue contour.
Mm-hmm.
The blue contour is constraints from real data from FIRAS. Okay. So if any power spectrum is lying outside these contours, this is already excluded now. Okay?
Right.
Now, if you take this is the kind of spectrum that is fitting the nanograph data. Okay. So if you want something to fit nanograph data, okay, it must take this form. Okay. Now, let us consider what kind of constraints we will get on this from Pixie. Nothing. We will just get upper bounds. Okay. So we will not be able to uniquely identify this. Okay. So we will produce a large spectral distortion. Okay. We will see this spectral distortion with Pixie. You can see it from here. So you see that mu is detected.
Right.
But we won't be able to tell that this spectral distortion is caused by primordial physics, okay? Essentially because of a redundance of the number of parameters, okay? We need, in order to model this, we will need like three parameters at least, position, amplitude, and width, okay? We won't be able to detect them all, okay? We will be able only to say that this region is consistent with a large mu type signal.
I understand.
Okay? That's what I'm saying. Of course, if you have a larger signal, okay, then you will be able to detect it with Pixie, but this is not what nanograph is seeing.
Okay.
Okay. But now, let us suppose that perform a joint analysis of PTA's data and Pixie data. Okay. Of course, Pixie data are mock because Pixie hasn't flown yet. Then because this is, you see, this is the nanograph contour, the green one. And so you see that the degeneracy lines are completely different, okay? So you will be able to break the degeneracies that you're not able to break with Pixie, and you will be able to measure all the parameters parameterizing this bump, and to constrain the power spectrum over to project the constraints on this power spectrum over a very broad range of scales.
Okay, maybe let me just rephrase my question, if you don't mind. Typically, if you look at some of these very broad plots trying to say spectral distortions will cut out this part of the power spectrum, and they will go up till 10 power 4 megaparsec inverse or so, many of them. What you're saying is that if I just have Pixie, I don't worry about PTA at this stage. It is not going to constrain until 10 power 4 megaparsec inverse.
It is not going to constrain until 10 to the power. No, this is precisely what you see in those plots. You see, I mean, this is what we are going to constrain until 10 to the 4.
Okay, it'll come until 10 power minus 6.
So you should imagine that the colored region is the allowed one. Anything else is constrained.
Okay.
Sure. Okay, and there's there's a caveat. Here I'm also considering Planck data. This is why you don't see these constraints rising up again, because I have another handle at large scales.
I understand.
Okay, but the right part of this plot is completely consistent with the kind of constraints you are talking about. Only here we are
added the PTA.
Yeah, and also the technicalities of our analysis are more. It's more robust because we are not taking. So usually these the works you're talking about, they consider these simple approximations for mu and y. We are computing everything with the green function approximation formalism with the Einstein-Boltzmann solver.
But you said those things, but K pivot will allow you some room, no?
Say that again?
The pivot scale will allow you some room.
Sure, absolutely, yes.
Okay.
But here we are basing our hypothesis is that the nanograph signal is there. So the idea is, can we tell something about the nanograph signal with spectral distortions? And the answer is yes, because there will be a synergy. Okay, so spectral distortions alone won't be able to detect it. They will indicate the presence of a mu type distortion. Okay, so let me rephrase it a different way. The signal from nanograph will inevitably produce a moderate mu type distortion. Okay,
so that will suggest a moderate.
Exactly.
Okay.
And in conjunction with Pixie, we will be able to detect this signal. Am I running out of time?
Okay.
You can take 3-4 more minutes.
Okay. Okay. Well, we'll just give an overview of the next part. So this was all from the observational point of view, and now I would have loved to talk a little bit about models that can produce this kind of features. Okay, we'll just give a very brief overview. So this is, for example, kind of a multi-field model that can produce this kind of feature. This is a very classical hybrid inflation type of stuff, okay, type of model. Only we have revised it a little bit together with some colleagues, and we embedded it in the so-called alpha tractor formalism. Okay, so essentially what happens, I don't know. Well, okay. Essentially here we have we have two fields. Okay, so we do not have only curvature perturbations. We also have so-called isocurvature perturbations. Okay, essentially there are perturbations in the adiabatic direction of the trajectory and in the orthogonal tangent and orthogonal direction to the trajectory. Okay, and what happens is that in this very specific kind of trajectory, so we have a single field like evolution, okay? And then at some point we have a tachyonic instability, okay? And the trajectory turns and it falls down this minimum, okay? And at this point, we generate a very large and negative squared mass for these isocurvature perturbations, okay? And so there is a super horizon sourcing. This is an example of what I was saying before. So in this case, we have that curvature perturbations do change on super horizon scales, okay? Actually, it is the isocurvature perturbations that grow on super horizon scales, and at some point there is a turn in trajectory, and this power is transferred to curvature perturbations. And so, yeah, we observe this kind of very large bump in the primordial power spectrum, which can be then translated into gravitational waves. And then there is, sorry if I'm going so fast, you can ask me technical questions at the end, of course. There are some pros and cons, of course, and but okay, another model that I have been working on with also Diraj and Sriram is this kind of two-field models where the two where we have two different stages of inflations again, and the two fields are kinetically coupled. Okay, and this kinetic coupling again at the transition between the two stages of inflation produces, but this is different from before, because before we had the large time where the square mass of these isocurvature perturbations was negative. Okay, so the isocurvature perturbations were growing on super horizon scale, and then there was a turn, and at that point, this power which was accumulated in the isocurvature perturbations was transferred to curvature perturbations. Here the situation is a little bit different because everything occurs around this turn here. Okay, so it's more of a violent kind of mechanism. Okay, and in particular, then I realized with Diraj, after this first paper came out, that okay, this is the sort of bump that we found in our first paper, and then we realized that this is certainly a very fine-tuned situation, but if the separation of scales between the first and the second stage of inflation is large, then you can have very violent oscillations of the first inflaton, and they can be translated into features in this power spectrum. Okay, but now the features are oscillations over many ranges in amplitude, and they can be translated, of course, into features, into oscillatory features in the gravitational wave background. Okay, and this is again, yeah, it is a little bit of a fine-tuned situation, but it's something that has prompted a lot of different works in the literature, and it's actually that we are testing right now. We are forecasting in the LISA collaboration, so it's something that people are taking seriously. And then there are canonical single-field models. Sriram and his students are experts on this. And let me just close with this model, which is something that I have been considered for a different reason. Okay, it's not that I am particularly fond of this model, but we used it as a toy model to explore something that after our work catched on quite significantly over the past year, okay, which is an issue with perturbativity, okay. Essentially what we are, so what I did before was to consider like the power spectrum computed from the equations of motion, right, the Mukhanov-Sasaki equations. And this can be shown to be equivalent as the tree-level computation for the power spectrum in the so-called in-informalism, which is what is used to compute perturbations during inflation, okay? But now one can ask the question, okay, but when you have such a large amplitude for the primordial perturbations, I mean, is the tree level the end of the story, or will the power spectrum receive some slow roll, some loop corrections? And this is a wrong diagram. This line shouldn't be there, okay? It should be just like a circle, okay? But you can see that you can get some loop corrections in principle, and we did compute them, okay? So we computed like 2 vertices loops in this model, and 1 vertex loops in this model. And the story is far more complicated than that, but this is more pedagogical talk, so we'll just show the results. And what happens is that we show that in principle these loop corrections can be larger than the tree level. And that's an issue. That's a significant problem, because that means that what people usually do, which is computing the primordial power spectrum at tree level, is wrong, because you can have a large contribution from loop corrections. And so we may need some more non-perturbative techniques in order to make predictions for primordial black hole production or gravitational wave production during these non-standard mechanisms. But this is not the end of the story. So let me stress that this was the first paper on the topic. Okay, so we were the first to consider loop corrections from a large amplification of power during inflation. But shortly after our paper, and in fact it was just 1 week after our paper, this very controversial paper came out. Okay, and this got actually most of the attention of the community. So this paper came out a year ago, and by now it has something like 80 citations. And this is way more controversial than what we did. Okay, so we essentially focused on the scales of the peak. Okay, so it is not, I think it's not controversial to expect that there would be some large loop correction at the scale, but the result of this paper is way different. So essentially they didn't even compute the loop correction at the scales of the peak, okay? And they considered large scales loop correction from small scales features, okay? And what they say is that primordial black holes, okay, the primordial black hole formation in single field is ruled out because the loop corrections from small scale physics are changing significantly the large scale power spectrum, okay? And because it was so controversial, this stimulated a huge debate in the literature, of course. I think that for example, we therefore concluded that PBS formation from single field inflation is ruled out is a generically wrong statement, of course, because this is, even if this was true, this would call for a non-perturbative analysis. And only after a non-perturbative computation of the primordial power spectrum, you would be able to assess that primordial black holes cannot form. So this last statement is generically true, is generically wrong, but I think it stimulated an interesting debate, and I think that some of their points are kind of correct. They should have probably put it in a more safe way, but the things are extremely complicated. And this is a slide from my old talk, so from a talk that I gave last summer. And so I was working with this friend of mine on this topic, and I gave this talk in June, and I said that we would have put a paper out in July, or at worst case scenario in September, and then we realized by working on that we were doing things wrongly, and so we delayed and delayed, so just not do that, please, don't do that. But the thing is, really, this is a very complicated area, so there are subtleties, and I'm sure that Sriram and his students know about that. We will probably talk about it over lunch. There's a huge number of subtleties in this area. And I think that there has been some advanced, I think, but my impression is that no one has really gotten to the point yet. So this is still something which is extremely interesting, and we were stolen the stage by this Cristiano in Yokoyama, but I'm happy that this is still a very interesting debate which is still ongoing. All right, so I could get to the end with a 10-minute delay. I can just leave you with the conclusions, and I'm happy to take questions.
Thanks, Matteo, for the nice discussions and questions.
I have a question about your comment on overproducing the PBH to match the nanograph observation. So when you consider PBH formation, there are some uncertainties, like how you choose the window function, what kind of collapse criteria you choose, like critical density contrast, if you consider. So if you consider those uncertainties, how would it affect the overproduction statement?
Yes. So what actually this is this line, okay, it corresponds to the standard choice of Gaussian window function, the standard value for the critical density of collapse, et cetera, okay? Yeah, now, but there has been several works, okay, adjusting the window function, adjusting the critical density, adjusting the amount of non-Gaussianities, adjusting like for example, whether your primordial black holes is forming during radiation-dominated era, or you could have some exotic kind of
equation of state
parameter. All these things, of course, will affect the amount of primordial black holes, and there are people claiming that this is still allowed, people claiming that it's not. Now, for sure, all these things cannot change. Even the drastic, like FNL equal to minus order 1, which will change significantly, right? Because what you care about in primordial black hole formation is the tail of the probability distribution. And when you have a large negative FNL, you probably know that, you suppress the abundance of primordial black holes. But even in that case, you cannot change the amount of primordial black holes. You cannot change the amplitude of the primordial power spectrum by more than 1 order of magnitude. Okay, and here we are saying that we go up to order 1 primordial amplitude for the primordial power spectrum. So yeah, it's still debated. The question is still debated.
Right.
But the problem is there, I think. And it's, of course, you would need to perform a full-fledged calculation taking into account all these uncertainties. But this is a large and worrying amplitude.
Okay. Okay. I have another question regarding your omega GW expression that you have quite earlier slide. At the very start of the expression, there is a 0.387 factor. Where is it coming from?
It comes from some weird normalization. Okay, this is, okay. I don't know where it comes from. It's probably, I have to check. I don't remember that, to be honest. It's probably a normalization of this convolution function.
Yeah, no, I remember exactly that factor coming from the G star factor that you have later, so.
Maybe, okay. But this is the standard, this is a pretty standard form, and actually not even sure that this is what I am, I mean, it comes in, this equation comes in many different forms. It also depends on whether you are considering this x, y variables or u, s, st. I mean, there are several conventions for this.
What if this, right?
Yes.
Yeah, right. One can do that. And about your, I have another question.
Sure.
So about the CMB spectral distortion, you have the bound from Cobefiras and you have the projected sensitivity from the PIXI.
Yes.
So when one can expect the PIXI to get some data?
Oh, that I don't know, to be honest, because it hasn't been accepted. That's the thing.
Okay.
It's just a proposal. So people talk about the 30s, like every other experiment. They talk about the next decade. They do not say that it's going to happen in the 2060, of course, but it's not sure yet. So this is, you can see this paper, I mean, I think this was, I mean, the original motivation behind this paper was one of the authors, which is my former PhD advisor, Fabio. He wanted to push, he's trying to push this spectral distortion thing. And so we thought about what to do, I mean, what we could test about primordial physics, and we came up with this. But still, it hasn't been funded, so I don't know.
Thank you.
Thanks for this excellent talk. So I had two questions. First of all is when you mentioned about this distortion from the perfect black body spectrum for the CMB. So is it a very new thing? Because previously we used to hear that CMB is a perfect black body. And how do we reconcile that with the...
No, CMB is not a perfect black body. Even in the lambda CDM scenario, these distortions are expected to be there. Let me show you.
I think that it's related, when you mean perfect, it's relative, right?
Yes, exactly.
Yeah, it's still a very good, like,
I mean, if you look at this picture, okay, these are the data with including the error bars, and you can see that they are even smaller than the width of the line, okay. So within these error bars, the CMB is a perfect black body, but the error bars could go down, and they could, actually what we get is an upper bound of deviations from this perfect black body. But even if within the lambda CDM, there is a guaranteed mu-type distortion and y-type distortions that are going to be there. So even if we assume our lambda CDM, if we had infinite precision, we would detect a deviation from this black body.
And what are these mu-type and y-type things?
So it's this kind of distortions of the CMB. So usually what you do, or the CMB spectral shape. So what you do, you classify. You can show that the exotic contribution. Actually, here I'm not including exotic contributions from very exotic types of early energy injection into the CMB, okay? This will create a different distortion, but again, this is what you would expect from lambda CDM. So from lambda CDM, you would expect these types of energy injection of spectral distortions of the CMB. You can break them into 3 different types that have this frequency dependence.
And what is the origin of it? So it is not a pure photon spectrum, but
no, it is the photon. I mean, it's energy injection from photons into the. So it's like this is like a.
It's a couple system.
It's kind of a Silk damping kind of stuff. Okay, so it's friction between photons that is turned into like energy injection into the CMB. And so, depending on the, let me see. So this, you see, this is the equation for the energy density of photons. And so you see that you have this source term here that is produced by small-scale density perturbations.
And one small question is, in your last part of the talk, when you mentioned about this loop corrections, this is for some specific choice of potential, or it is there for any choice of potential?
Yeah, good question. So what we had in mind initially was to provide like a comprehensive analysis. So I'll say some sort of generic statement, okay? We couldn't do that because things are extremely complicated, and so we considered this model. Let me show you. A model where you have this type of oscillation in the primordial power spectrum. Then the controversial paper and all the other papers that followed, they considered a different thing, like this one. Well, not exactly this one, but similar to this one, okay? Like an inflection point in the potential, okay? And I would say that they are related, of course, to each other. This one is probably a little bit more complicated to study than what we did. Because of some super horizon. I mean, it's a complicated issue. So what I said is that it is controversial to expect some large scale effects from small scale physics. In fact, this model is well known to provide some way for the perturbations that are super horizon to evolve. So you do expect some large scale, some effects on large scales from small scale physics, but it is, I mean, the separation of scale is so large that it becomes controversial. That's the point. So yes, so there is no, at the present time, I think there is no consensus whether this is a generic thing of all the models featuring a large scale, a large amplification of power. But I would expect, I mean, I would say that at least you should check that. And it's not easy to check at the moment because people do not know how to compute loop corrections during inflation.
The challenge primarily lies with the fact that your coupling functions are all very time dependent.
Yes.
That's the challenge.
Yes.
To speak in a field theory language.
There is another challenge. Any of those distortions that improve your prediction, are they normalizable?
Renormalizable, you mean, is the potential itself renormalizable?
Yeah.
No one considers potential to be renormalizable anymore.
No, but it is possible to do it. We have written a paper about a decade back that there is a generalization of the Stravinsky model, which includes the Ricci tensor as well.
No, but this is a different Stravinsky model.
I know, but that modification is renormalizable, and that doesn't distort any of the results that you have classically below the Planck scale. Above Planck scale, it is renormalizable, so everything more or less goes through completely.
So those kind of models typically will
that's only one model.
those kind of models typically lead to only slow roll effects.
Exactly.
That's true, but
he's talking about models which are more complex.
No, the tadpole effects do not distort your classical result. See, the difference is the loop correction, the quantum corrections make a big distortion if it is a non-renormalizable theory. So but they don't make a big distortion if they are renormalizable.
Loop corrections to zeta.
Yeah, we are talking about loop corrections to a different quantity, I believe, in contrast to what you are referring to.
No.
These are loop corrections to perturbations, not at the background level.
Okay.
These are a different kind of loop corrections.
No, they are related because you can take the loop correction to the effective action and then take these perturbations. Nothing changes except...
You are talking about perturbations of the background, which is the smooth background. We are not talking about that. What Matteo was talking about is loop corrections to the curvature perturbation.
But then where are you taking the quantum corrections coming from that or not? Because I saw the tadpoles being referred to.
I think we need to discuss this on a blackboard.
Sure.
Thanks for this nice talk. Actually, I have a question from part one. Sorry. So you discussed, I'm not from this field, so it might be very silly. So you discussed about, showed this landscape to show this slow roll inflation and said that there is this massive modes on the orthogonal direction. And your FLRW equation had this field variables which is just one time, means dependent only on the time. So I was trying to understand these massive modes in these phis. What does they represent? Do they represent some inhomogeneity which you assume to be zero, or is it something else or some oscillator?
You can compute them to be zero. If you have if all the massive directions are stabilized, you integrate them out, okay?
No, what do you mean by the massive modes in these 5 fields? This is my question.
So they are like this. Let me show you. Okay, I don't have the formula. So you could have like massive fields, like you add other massive fields, phi with a potential like m squared, phi squared. Okay.
Yeah, but now you have 1 dimension, right? Not 2 dimensions.
Yeah, exactly. No, you start with 2 dimensions, okay? Those fields they lie at the bottom of the potential because their mass is extremely large, so they are stabilized at the bottom of the potential, okay? And they just do not participate in the dynamics, okay? So essentially you're only interested in one single dimension because all of the other fields, that is the other dimensions, they are not contributing to the dynamics.
And these 2 dimensions that you consider includes a time direction, right?
Say that again?
The 2 dimension that you consider also includes a time direction, right?
No, sorry, I'm talking about dimensionality of the field space. Phi, you have scalar fields, okay?
Yeah, understood. I was actually trying to understand this phi variable which you said that is independent of x when you assume homogeneity and is only dependent on time and which actually changes across time.
No, the space-time has 4 dimensions, 3 spatial dimensions and 1 time dimensions, okay?
Yes.
So in the context of inflation, the whole point about inflation is that you have to wash out any initial homogeneities, okay?
Yes.
And you want to end up with the space-time which looks like a unperturbed FLRW metric, okay? So you want isotropy and homogeneity, okay?
Yes.
Then on top of that, you can, of course, inflation generates also some inhomogeneities, but at the zeroth order, you want isotropy and homogeneity, okay?
Yes.
So the scalar field has to depend only on time.
Yes.
Okay?
Yes.
And it is possible to have a configuration of the scalar field that depends only on time, which I showed at the very beginning of my talk.
Yes.
So here we are talking about space-time dimensions, okay? Then I moved back and I looked at the dimensionality of the field space, okay?
I see.
Dimensionality of the field space means very loosely
so
how many fields are there.
Yes. I see. Mm-hmm. I see. Okay. Thanks.
Any other questions? So if not, let's thank Matteo.